Hello, welcome. We're going to do 13.4, motions in space, velocity acceleration. Let's get to it. Paper view, and we'll zoom in the wrong way. Okay, scissors out of the way, stapler out of the way. Motion in space, velocity and acceleration, that's what we're going to check out. Suppose a particle moves through space so that its position vector at any time is given by this. As a function of t, a function f of t, g of t, h of t, or you could write it in IJK notation. Either way is good. And so we've been looking at this throughout the whole chapter 13. And in fact, I think even in 13.1, they told us if you wanted to, and remember, this is a space curve. And so like it represents how an airplane would go along. I kind of think of it as when they ride in the sky riders ride in the sky, and they leave that little trail of white that you can see. I kind of think of it as that. I like to think of it. So if I wanted to find the instantaneous velocity, the velocity is the rate of change of the displacement per unit time. And yep, that means it's going to be a vector. The velocity gives you the direction of the speed, and the velocity is equal to the first derivative of your, this is your vector that tells you where you're at, right? It keeps pointing at it, pointing. And so the acceleration is the rate of change of the velocity with respect to time. Acceleration is a vector quantity that is defined as the rate at which an object changes its velocity. An object is accelerating if it's changing its velocity. And the acceleration is the second derivative. And good news, we already knew these things, right? And so it's lucky that they're not something different. And then speed is the absolute value, in this case, the magnitude, since it was a vector. So the magnitude of the velocity. And I said speed needs a cool symbol. And so we're going to look at some examples here. In 2-dimension, you can draw things, and so that's kind of nice. And so our first example here is in 2 dimensions, whereas in 3 dimensions, it becomes significantly harder to draw things, and so that you can kind of look at what you found. So it asks us to find the velocity of the particle, and so I know the velocity of this particle. It's a vector, and it's given by r prime of t, and that's a vector. And let's see here. So easy, right? The derivative of 2 is 0. The derivative of negative t is -1. And the derivative of this, you can think of this as 4t to the half, of course. So that when you take the half down in front, you get 2 t, right? This would be when I take the derivative, 2t to the negative half. And then if I write that in better notation, 2 over the square root of t. And so that's how I want to write it. And then they asked us to find the acceleration of the particle. So if I want to find the acceleration of the particle, so easy. It's the second derivative. I have the first derivative here. So it's 0, right? The derivative of -1. The derivative of this, now I might be better off looking at this. So take the half down in front. So that's going to give us -1, right? So -1 t to the, and then take away 1 here. So -3/2 t to the -3/2. So I'm going to write it like that, -1 t to the -3/2. And yeah, it's a vector. And then they asked us to find the speed of the particle. I'm going to write speed. Speed is the magnitude of the velocity. So that's the square root of, and then square this, so that's 1. Should I do this like that? Would that make me happier? I don't know what would make me happier today. It's one of those days. So I'll look at that. So square the pieces there. And so I'm going to have 1, and then I'm going to have, so here I'm going to have 1 plus 4 over t. And I might not be able to help myself but get a common denominator and make that look a little bit better. I don't know. I think that it makes me a hero when I simplify things up a little bit. Makes UC Berkeley proud of me. Makes them want to accept me into their school. I was kidding. And so you don't want to go to Berkeley. You want to go to Cal Poly SLO. Let me show you. Yeah. See, you want to go to Cal Poly SLO. That's where you want to go. Just kidding. You can go wherever you want. Wherever you go, be happy. Just be happy where you go. Okay, so this would be then the square root of t plus 4 over t. And that was the speed. So lovely job on that. Now they're asking us to sketch the path of the particle. So we'll go back here and see if we can sketch the path of the particle. So we need values for t to put in, right? I'm going to put those right here. So if I said that t is equal to 0, then we're going to get, that's going to go with, it's going to go with this vector here, 2 and then 0. But remember what you're going to, so I'm going to plot that 2 over 2, 0. So that's here. And this is that vector right there. But what we're just looking at is the point. And so that's going to create a curve for us. I can plot a bunch of points, right? Like I could do t is 1. When I do t is 1, I get here. And I'm going to show you that, hey, I want to do something different than this maybe. So this gives me 1 and then 4. And so over 1 up 4. And so here's another point. And the vector is pointing to that. And so I have 2 points on it. And I don't know, is this thing a line? Is it a curve that looks like a snake, a curve that looks like an absolute value, a curve that looks like, that'd be like a straight line, right? Absolute value makes a V. I don't know why I said that. It would be a curve. If I want to know what it is, then what you want to do to figure out what it is, Kevin says it's snowing in Tehachapi, is that x, our x coordinate right here, x equals 2 minus t. And then our y coordinate is 4 square roots of t. And then if we wanted to put these together, well, this would be x minus 2 equals t, or negative x plus 2 equals t. And then you can put in here t, right? So this would be y equals, instead of t here, x minus 2. So this would be 4 times the square root of negative x plus 2. And then now, I kind of know, I got off the page. I kind of know what it looks like. It looks like something that is my square root friend, right? And so normally things that have a square root in them look like this, that this is y equals the square root of x. And I could do a bunch of transformations and whatnot. I probably am not going to do a bunch of transformations. That's probably not what I would do. I would probably, with my knowledge that this is the basics of what the graph is going to look like, I would probably get a few points on the graph. So I already have here x and y. I already have, and I've already plotted when x was 2. When x was 2, y was 0. And you see we got that point right there. And I've already plotted when x was 1. Well, that's the square root of 1 times, which is 1 times 4 is 4. Now I would be very much interested in plotting if I was to let this be 0. Should I go 0? Should I go negative 2? Because I want to make it nice underneath there. Negative 2 will make it nice underneath there. If I go negative 2 underneath, negative of negative 2 is positive 2, plus 2 is 4, and the square root of 4 is 2. 2 times this is 8. So here at negative 2, 1, 2, I'm up here at 8. And now And I'm going to erase where I drew my vectors to show that it was pointing in. And so now you can kind of see my curve in here. Do you guys agree that I shouldn't pick anything when I'm picking points here, that I shouldn't pick x is 3, because if I do, I'll have -3 plus 2. So 2 was the very last thing that I should be picking. So I've done a lovely job at sketching the particle's path. Now what they want me to do, so I did that, sketch the particle's path. Should I put arrows on it to show that it's going in? I guess I put an arrow here at the end. But here at so this is the direction it's going in. Okay, so I now have arrows on there. Draw the velocity and the acceleration vectors for t equals 1. So the velocity vector for 1 is -1, and then you're going to put in here 2 over the square root of 1, because you're plugging in. You can't see, I'm sorry. So I'm right here in this vector right here for the velocity, and I'm plugging in 1. And I can make this a little bit backed up, wrong direction, right? So I'm plugging in here 1. So when I plug in there 1, the square root of 1 is 1. So this vector becomes -1, 2. I'm going to also find the acceleration vector at 1. So I'm going to come here to here where I found it, and I'm going to plug in 1. Now 1 to the -3 is equal to 1, and then times -1. So this is equal to 0 and then -1. And then I'm going to plot both of these vectors, and then I'm going to move them just so that you can see. So from the origin, -1 up 2, so there would be that vector, but I can move that vector anywhere I want. That's the velocity vector. And where I want to move it is to where t is 1. So right here is t is 1. And I'm going to move that vector. So it was over 1 up 2. And I'm going to draw it in here. Now I could do that with all, so you can hardly see it because it's almost on my curve there. I could do that with this other vector. I could draw it. Here it is 0, -1, so it's not very long. It's right there. And it's going to be right here, 0, -1, because they asked me to draw it on there. There it is. So we did a lovely job at that. And then I want to 0, -1. Donna, did you draw that wrong? Yes, you did. Over 0, down 1. It should have been going down. Why did I draw it like that? I don't know, because I'm maybe frustrated with how much time it took me to get going on the video. No, that's just an excuse. Preoccupied by my tea? No, that would be an excuse. Don't use whiteout. It'll just mess it up. Okay, so velocity, where did it say? At 4. And so we're going to be plugging in right here 4. I think that was probably nice of them. Square root of 4 is 2. So this is -1 and then 2 over 2, which is 1. And then acceleration at 4. T to the 4 to the, let's put that in our calculator. So 4 raised to the -3/2. And we get -1/8 because it's -1 times that, which was 1/8. So here we're getting 0 and then -1/8. And I'm going to plot that on here. Are you going to focus? Too close to focus? Okay. And so we're going to be here at t is 4. T is 4. I'm sorry, I didn't say this before on the other one, and I wish I would have. When t is 1, that means that x is 1 and y is 4. And I just kind of got lucky because I came over here and said, well, if I go over 1, but that was not thinking. It was lucky. And so, but I knew that I wanted to be on my curve there. So when t is 4, x is 2 minus 4. So 2 minus 4 is negative 2. So if I want to plot this, and the square root of 4 is 2 times 4 is 8. So we're at this point over here, negative 2. There it is, 8. That point right there. And we're going to draw the velocity vector on there, which is from here. I'm not going to mess it up this time. It's slope, right? And so don't forget negative 1, 1. And so we're going to go this way, 1, up 1, up 1, and draw it in there. And then 0, negative 8. So from this point right here, we're going to go over 0. That means don't move at all. And then down 1/8. So it's just barely that way. Down 1/8. So we drew it on there, the velocity vector and also the acceleration vector. Okay, so we did a nice job on that. We could find the speed at these different places. It didn't ask us to, but we certainly could. If they wanted to know the speed when t is 1, we could plug it right in here, and that would be the square root of 5 over 1, right? Square root of 5. And when t is 4, that'd be 8 over 4 is 2, the square root of 2 would be the speed. Okay, so we did a lovely job on that. So that's example 1 on my new numbering them scheme. And this over here is example 2. It gives us the position vector here. It asks us for the velocity of the particle. So we know the velocity of the particle is equal to the derivative of the position vector. And so, great. And so the derivative here of is 2t I and 2j, so not very hard. And then what's the derivative of the natural log of t? I hope you're shouting out your screen. And something I know just right here before I even go on is because I have no problems with the domain for t squared. No problem. The domain is t. No problems with the domain for t, but for natural log of t, there's a domain issue. And so because of the natural log of t there, I know that anything I say about this is only good for t is greater than 0, because the natural log of 0 or a negative gives you error, right? And so we notice this about the domain. And so that whenever we're working along, they didn't say anything about the domain, but we noticed that that's the case about the domain. And then the acceleration of the particle, that gave me quite a lot of room here. That's not normal that I get so much room, but I'll take it. And not a very hard one either, right? So this is 2 I, and then 0 on the j, so you don't have to write it at all. And then if you take the derivative of that, so if you need to write it as t to the negative 1 to take the derivative of it, great. So that when I take the derivative of it, I'm going to get negative 1 t to the negative 2, which is equal to negative 1 over t to the second. Maybe that's how I want to write it today. So negative 1 over t to the second k. And so we did a lovely job at that. Then they asked us about the speed of the particle. And we remember that the speed of the particle, speed, is equal to the magnitude of the velocity. So you can imagine the only thing that would make this harder is harder to take the derivative. I mean, it's not hard at all. And so here we're doing the magnitude. So it's that squared. So this is 2t squared plus 2 squared plus 1 over t squared. 1 over t, and I squared it in the wrong spot, but actually I got lucky and it was right, but not, that wasn't on purpose, but it was right. If I mess around with this a little bit, 4t squared plus 4 plus 1 over t squared. And if I get a common denominator, actually it's going to turn out quite nice. And I'm always asked, should I simplify things? And the answer is yes, you should, definitely. And so when I get a common denominator here, this is going to be over 1 here. So times t squared top and bottom here. So that's 4t to the 4th over t squared. You know, this is the place where I needed the room. And then over 1 here. So 4t to the 2nd over t to the 2nd plus 1 over t to the 2nd. Don't worry, I'll just go beside this joke that's down here. And so here we're going to get the square root of 4t to the 4th plus 4t to the 2nd plus 1 divided by t to the 2nd. And I'm going to go right here. I'm out of room. This thing, I don't know if you recognize it, but it factors. And how it factors looks like this. 2t to the 2nd plus 1. It's a plus 1. Times 2t to the 2nd plus 1 divided by t to the 2nd. And yes, this is still the square root. This is equal to the speed. Just had to go on the side of my paper. I ran out of room. And I'm not writing where you can see me very good. But good news, that's a perfect square, the numerator, because they're equal to one another, right? If you needed to, and it made you feel better, because that's how they wrote it in your algebra class, like this, 2t squared plus 1 quantity squared over t squared, like that. You could do that. And then the square and the square root undo one another. And technically, I should have absolute value around that. I'm not sure if you guys remember that the square root, I'm going to put it over here, of x squared is equal to the absolute value of x, is what it's equal to. And that's essentially what I have, right? Is I have this squared, so you put the absolute value around there. So technically, I should have the absolute value around here over t, the absolute value around that for the speed. But I'm going to tell you why I don't need the absolute value. Not all of the problems that I do, I don't need the absolute value, but I don't need the absolute value because this is squared. So it's always positive. Times a positive, always positive. Added with a positive is always positive. Then you might be saying, well, t down here in the denominator is not always positive, but do you remember on the domain what we said? We said t is always positive. So in this case, if I didn't put the absolute value, I would get away with it and have been lucky. And but it would just be a coincidence. Mostly I need it. Okay, so there's my answer right there. So there's my speed. And we did a lovely job on that. It's actually a problem in your book. This one right here. It's in the Stewart book, it's 13.4, problem 12 is what it is. And so anyway, so that's the story on that one. Okay, so we did a lovely job on that one. And now we're going to look at, what are we going to look at? Tangential and normal components of acceleration. So when a body is accelerated, it is often useful to know how much of the acceleration acts in the direction of the tangent vector and how much acts in the direction of the normal vector. And And so then they've tried to, I've got this picture right out of your textbook, is what I've given it. And they say that AT, if you're interested in how AT, and that's the acceleration in the direction of the tangent vector, and AN in the direction of the normal vector are found, you can go check that out in the book. So they go into detail on that. And so the tangential component of acceleration is the rate of change of the speed, and the normal component of acceleration is the curvature times the square of the speed. This makes sense if we think of a passenger in a car. A sharp turn in the road means a large value of the curvature. So the component of the acceleration perpendicular to the motion is large, and the passenger would be then thrown against the car door. And so just think about that the next time that you're out riding in a car or riding on a bus or whatever have you, and it goes around a curve at a speed a little bit, maybe a little bit higher than normal, and then you kind of get thrown towards the door of the car on that. High speed around a term has the same effect. And in fact, if you double your speed, AN is increased by a factor of 4. So if you go around a curve way faster, doubling your speed from the previous time you did it, then the acceleration towards the door, perpendicular, is times 4, is what it is. So anyway, so that's kind of the story there. I just took these formulas right out of your book. You don't have to memorize them. And there's times when it's convenient to use this, depending on what you know, or this, or this, or that. I mean, depending on what you know. So that's the story on them. So it's probably a good idea to have all of the forms of it so that you can start saying, well, what do I know? And then you can figure out which one would be the best to use based on what you know. Okay, so that's kind of the story there. And so we're going to do some problems here. A problem here, at least one problem here. An example problem, example 3 in my notes on page 28. So we have then, oh, this is the same one, back to that crazy particle with this position function. And so they're asking us to find the tangential component of the acceleration. And so I'm looking at my formulas. So I'm back here looking at my formulas and thinking about, well, what do I know? And so that I can use what I know. I look at this and I think, well, easily I know R prime and not R double prime. Actually found those in the previous problem, I believe. And then dividing by the magnitude of R prime. And I believe I also found that because that's the velocity, right? The magnitude of the velocity. So I think I have all the pieces that I need for AT already, that we found them in the previous example. And so you can go check it out and make sure. So I'm going to write my formula right here, AT, and I'm using this part of the formula, dot product here. So we found this before, and we said that it was, and you can go look it up and you can verify 2t, 2, and I think we wrote it in IJK notation, and now I'm writing it in vector notation, but same guy, right? And so, and then dot product, and then we also found R double prime. If you wanted to, you could find it right now. You know, the derivative of 2t is 2. I mean, you could have found this here. The derivative of t squared is 2t. The derivative of 2t is 2. The derivative of the natural log of t is 1 over t. I'm going to make a note that t is greater than 0 right now on my domain, just because I'm worried that it might come up again and I might forget it. So the derivative here is 2. The derivative here is 0. And the derivative here was negative 1 over t squared. And then the magnitude, well, what do I want to find the magnitude? I want to find the magnitude of this. So that is the square root. And I believe I did so much work on that and I simplified it so much. Do you guys remember what I got? I got 2t squared plus 1 over t. This is when I really care. This is when I really care that I don't have the absolute value around that. Because if I had the absolute value around that, it would be difficult to simplify this. So when I do the dot product and I multiply those together, I get 4t. I multiply these together and I get 0. I multiply these together and I get negative 1 over t to the third, all divided by this. And of course, I should simplify that up and make it look nicer, right? Naturally, I would want to do that. So what I would have to do that would be multiply. You got this complex fraction in the numerator and a complex fraction in the denominator. And the lowest common denominator, least common multiple between those complex fractions is t to the third. T and t to the third, the LCM is t to the third. So you would want to multiply everything, top and bottom. So I'm going to multiply in the top by t to the third. And I want to multiply everything in the bottom by t to the third. And that should make everything a little bit nicer. So when I multiply this by t to the third, I get 4t to the fourth. 0 I'm going to ignore, and then minus 1. And then in the here, right, I'm going to go ahead and allow myself, just because I can see what's going to happen. Can you guys see what's going to happen right here? This thing's factors, right? My algebra students were factoring these the other day, and they weren't happy. I'm going to factor it so you can see that right there. So when I multiply this by t to the third, the t and the t to the third cancel with one another and give t to the second. So I'm going to write this as t to the second times 2t squared plus 1. Just kind of seeing that, well, I had a difference of squares in that numerator right there. So this right here is t to the second over 2t squared plus 1. And those cancel out. So that at equals 2t minus squared minus 1 divided by t squared. So we did a lovely job on that. And we'll go look in the back of the book on that one, because I think this problem was a problem in the back of the book. And definitely it is. Okay, so we did a lovely job on that one. I hope I should have made more. I made more room, told myself to make more room, and I did make more room, but now I'm wishing, as big as I'm writing today, that I would even made more room. So if I want to find the normal, this is the formula for it. So I'm going to have to do a cross product. And I already know the magnitude here, but I'm writing my formula down anyway. So there's my formula. I think I'll put my cross product right here. My house is really cold. Freezing, freezing cold. So this one, right, 2t, right small, Donna, right small, 1 over t. 0. Oh, I love it when there's a 0. That makes things easier. Okay, so when I find I don't know, I like to do that. So when I find I, I'm going to get this one here, which is negative 2 over t squared, and then minus 0. And I'm going to scoot that in because I'm going to run out of paper over here. And I'm going to scoot this in because I'm going to run out of paper over there. Negative 2 over t squared I minus, and then j. Now j is going to be both. So this is going to be 2t times a negative. So it's going to be a negative, and then 2, and then over the t squared is going to be over 1t. Now I'm praying for not making a mistake. So minus, so this would be minus 2 over t j. And I'm going to have to put k here, plus, and then k. So it does go plus, minus, plus. I was seeing a lot of mistakes on that on your cross product. So fix up your cross product. So here I'm going to get negative 2 over t squared k. So when the dust clears here, and we see what we've got, I'm going to write it right here, my cross product. Should I put it right here? My cross product right here. This cross this. Is it okay if I just write it like that? That cross that equals, and I'm going to write it as a vector. So it's negative 2 over t squared, comma, and then it's a negative 4 over t, and then times the negative is a positive 4 over t. I made a mistake on this last semester. Right there, I made a boo-boo because I have a sign error. And then here, 2t, put your finger on k. Do you see the mistake I made? I think I had my finger on the wrong one. And I think it was because I was complaining about people make a mistake on their cross product. And I was about to make a mistake on my cross product. And okay, so I'm going to put my finger on here. 2t times 0 is 0. And then minus 4t, minus 4, no t, minus 4 is what that should be. So this would be negative 4 on k. And I did have a sign error though last semester, and I always find mistakes every time find a mistake if you're not careful. So I'm going to look at the magnitude of that. So I square this, and this is why I didn't know I had a mistake on this part last semester, because I made a sign error and then I squared it. And so I got lucky. And so this is the part that's it's just going to take a little. This is my numerator, right? And so that's why I'm finding it, and then divided by, that's my denominator, and I know what my denominator is. So this is just going to take a little bit for me to simplify this up and flex my algebra skills big time. My algebra muscles will be flexed right here. And plus 16. And getting a common denominator, which would be t to the fourth. So t to the fourth already here, multiply by t to the second, top and bottom here. And I'll write that over 1 and multiply by t to the fourth, top and bottom here. Same thing that you saw happen in the other one is going to happen here. It's like a miracle problem. It's like it really simplifies nicely. And so, and should we simplify things? And the answer is yes, unfortunately, we should. So when the dust clears here, I have the square root of and then 16t to the fourth plus 16t to the second plus 4 over t to the fourth. And that numerator there, you might not recognize it, but it's actually a perfect square. So the denominator t to the fourth, you recognize that is a perfect square, but the numerator is also a perfect square. You could factor out a 4 first if it made you happier, and so I will. It makes me happier, probably. And so this is 4t to the fourth plus 4t to the second plus 1. And I hope that you recognize it now that I've done that, because we've already factored that one, almost factored that one. And so this is going to factor as 4, and then 2t squared plus 1 times 2t squared plus 1 over t to the fourth. That was the hard part in all of the calculus for me, was my algebra. And the thing I would say, so that's why I laugh at students when they say it to me, is, well, do we have to simplify it up? And because the reason I said that is because I couldn't simplify it up. My algebra was so bad. And so I always recommend that calculus students go and tutor algebra students. I always recommend it. And I had a calculus student one time, a Calc 1 student asked me, well, how much should we charge them? And I said, well, you shouldn't charge them anything. You should pay them for allowing them to practice your algebra on them. By teaching them algebra, you should be paying them. And he's like, well, how much should I be paying them? And I'm like, well, $20 an hour and a pizza, I think, would be perfect. Anyway, I know I'm kidding. So the square root of 4 is 2. These are repeated, right? So you could write this as 2t squared plus 1 squared if you like. So when you take the square root of it, you get 2t squared plus 1 over t to the second. And then now we're not tempted to put the absolute value around it, because even though the absolute value is technically there, but we're not tempted because everything's positive, because t squared and whatnot and all of that good business. But maybe I will get rid of that. You're saying to me, I hear you. You're saying, but you haven't done the whole thing, and you're totally right. And I'm almost out of room. So I'm going to have to erase this and wish that I would gone over here. So I'm going to put thus right here, thus, because remember, this is what we were trying to find. I almost forgot what I was trying to find in my craziness. So we just found the numerator. And this numerator, I'm going to write it without absolute value. So this numerator right here is 2 times 2t squared plus 1 divided by t squared. So that's just the numerator of my thing. Right? That's just the numerator right here that we just worked really hard just to find that numerator. And man, we needed more room. Do I have more room on the other side? No, I don't. Okay, sorry. To everyone here that are not real students, because the real students are coming next semester. I'm just kidding. I don't have Calc 3 next semester. The real students will be Calc 1 students, divided by this. And good news, we found that, right? We had found that up here, right here. So we're going to put that right here, 2t squared plus 1 over t. And here you're going to see a miracle, right? So we have them stacked, as you can see. However you want to do it, the 2t squared plus 1 is going to cancel out with one another. And so if you want to write it as a division and then cancel it, or however you do it, I mean, you do you on that. I'm saying, well, they're both in the numerator, so they cancel with one another. These are both in the denominator, so they cancel. That's what I would say. So they cancel with one another and leave just t down in the denominator. So this would be an will equal the 2 in the numerator right there. And when these cancel with one another, you get just t. So this thing cancels down to 2 over t, as nasty as it was. And so that's why you want to simplify. You don't want to give someone some nasty formula when it does simplify down to be so nice. And so, oh my gosh. Okay, we did a good job on that. It was lovely. It was beautiful. It was kind. It was friendly. Um, so now, example 4. Too many examples, maybe? I don't know. Didn't seem like that much when I was reviewing it. So it says find the position vector of the particle. And oh, this is one of those initial value problems, is what it is. So in order to go backwards, I'm going to have to integrate. So good, good, good. And so what I need to do is I need to integrate. Integrate. How do you spell integrate? I don't know. So if I integrate acceleration, you get velocity. Just kidding. And then if you integrate e to the t, you get e to the t. That's pretty good. If you integrate e to the negative t, then you get negative e to the negative t. Do you guys agree? This doesn't have a j, does it? Okay. Plus c. And so then we can use our initial value here. So we know that the velocity at 0 equals, now if we put in t is 0, e to the 0 is equal to 1. So this would be I. E to the 0, negative 0 is 0, is 1. So this would be negative k plus c, the vector c, right? And that equals, what did they say that it would equal? They said it would equal I plus 2j. I plus 2j. So you can solve this for c. You would take away I from both sides to solve for c and add k to both sides. Solve for c, so that we know that c is equal to, the i's go away, 2j plus k. So we did a lovely job on part of it. We haven't done the whole thing, but we're gonna go and do the whole thing. And so what this means, so remember, this is what we said about v. This is what we just found about c. So I'm going to put that right there. So v is velocity equals e to the t I minus e to the negative t k plus c, which we just found was 2j plus k. And then we can combine, the k's together anyway, and put the j where it normally goes. The j where it normally goes. So this is going to be our velocity. E to the t I plus 2j. And then on the k's, this is 1. So this is 1k right there, right? So I'm going to have plus, and then I'm going to write it this way, 1 minus e to the negative t k. That was a 1 right there in front of them. So I just pulled out, there's a 1, right? And so I just put it, and I decided to write the 1 first. I can write either one, it doesn't matter first. And I essentially factored out a k, is what I essentially, if you want to think of it like that, would be wonderful. We did a lovely job, and now we got to integrate. That's how you spell integrate. I don't know. I'm crazy tired. So when you take the antiderivative of the velocity, you get the position vector. When you integrate that, you get e to the t I. I love that one. That's pretty easy. 2t. That one's not too bad either. J. And then here I'm going to get plus, and then this is t. And then this would be plus e to the negative t, and then k. Okay. So plus, I almost forgot, a constant. Okay. And then we knew from being given r at 0 equals, so now I'm plugging in t is 0 right in here. T to the 0, e to the 0 is 1, so this is I. So this wipes out the j's, so they're gone. 0 wipes out that, but this is 1. So this is 1k. Is that okay? Wiped out everything except for 1k. So k plus d, and which is a vector. And remember what this was equal to, r at 0. R at 0 was equal to I plus k. So this is I plus k. And I feel really awkward because d is 0 then. Do you guys agree? And so we know that d equals 0. Now, be careful because I'm putting that like that, but I'm being uncareful. Do you agree? It's a vector. And so to be more careful, maybe I should put the vector on top of it. And so I'll say to myself, ha ha ha, be careful here, right? And so now, but I guess it's okay. So here we go. R at t then equals e to the ti plus 2t j plus t minus e to the negative t k, and then plus the 0 vector, which wouldn't change any of these other pieces here. So actually, that made it a little bit nicer, actually, made it better. Okay, we did a lovely job on that. And now, this is all there is at chapter 14. Chapter 13, excuse me, chapter 13. Sorry. Okay, last example here is projectile motion. Get it on the screen. Just to get an idea, we make it easy and ignore that we are on Earth with air resistance and wind and changing air density. So just to make it easy, this is the formula if we ignore all of those things, right? And so this is the vector ij, so of some projectile. And they say where v naught is the initial velocity, which would be speed. Alpha is the angle of inclination from horizontal. H is the height if the motion starts on a cliff, etc. If it starts on the ground, 0 then. G is the gravitational constant, which is either 32 feet per second squared or 9.8 meters per second squared, depending on if you have your other stuff in feet or in meters. And so your height then should be in feet or in meters, and your velocity should be in meters per second or feet per second, and your time should be in seconds. So then the range, this is the distance the particle has traveled at a given time, is given by this. And that's just this part right here, which is the t, that's the x. And then y is the height of the particle at a given time. So that's right here, all of that, j. So, and then I tell you, this is a really cool example about a spud launcher, a building, and a potato. And so if a potato is launched from the top of a 176 foot, of the 170 foot, 6-foot Stockdale tower, if the launch angle is 30 degrees and the initial velocity of the potato is 160 feet per second. And so now that's all the information that we need, right? Now we're going to start answering the questions over here. So I'm going to leave my booklet open, move my water, move my tea, move my throat lozenges, everything I have here, so that we can. So they asked me for the range of the potato. So the range of the potato, I don't know if you're remembering, but the formula for the range of the potato was x equals v naught cosine of alpha multiplied by t. And so if we start thinking about, well, what things did they give us? And so, well, they gave us the velocity. They said that it was 160, the initial velocity, they said it was 160 feet per second. So I'm going to put that right here, 160 feet per second. And then cosine of alpha, alpha was the angle that it was launched at. And they said that was 30 degrees. And so this would be cosine of 30 degrees. Tyler says it's colder than 30 degrees in Tehachapi. And then times time at any given time. And so he said it was snowing a little bit and really cold. And he was sad because I made sure my calculator was in degrees because he left here from Bakersfield and he was wearing shorts. Not that it was that warm here, but I'm freezing actually in my house right now, but he was wearing shorts anyway. And then got up there and was shivery. So 160 divided by 2 and then times the square root of 3. Well, I can just times the 160 right here on my calculator. What am I doing? And I get 80 square roots of 3. So x equals 80 square roots of 3. Help me with my units here. Time will be in t, so I need t here, times time. Time will be in seconds, so the seconds will cancel out, and so this will be in feet. So that's x. And then what is the height of the potato? And I really wish I would have had more room here. But you know how that goes sometimes. So this is y equals, and this is the height, h plus, this is the initial height, v naught sine of alpha times time minus 1/2 gravity time squared. Okay. So the height, the initial height was 176 feet. The initial velocity was 160. I'm going to put feet there. Plus the initial velocity was 160 feet per second. And then sine of 30. And then t minus 1/2. And then because this is in feet, we're using 32 feet per second squared times time squared. So y equals 176 feet. And then sine of 30 is surely half, right? So this is 160 times the sine of 30, which is going to be half, right? So this is going to be 80. And then the time has seconds on it. So that'll cancel with those seconds. So this will be in feet. So this will be 80 t, and that'll also be in feet. And then here, we're going to have half of 32. Half of 32 is 16. Time squared is in seconds squared. So that will also be just in feet. So this will be minus 16 feet. Oh, t squared feet. So this whole thing is y equals 176, they're all in feet, 80 t minus 16 t squared. All of this is in feet. Okay, that would be our units there. Okay, and then it asks, when will the potato hit the ground? So this is the height of our potato at any given time. This is how far our potato has gone from the starting position at any given time. And they want to know, when will the potato hit the ground? And so Do you know how far the potato would be away from the range of the potato? How far it is from the starting position when it hits the ground? And the answer is no. Do you know how high the potato is off the ground when it's hitting the ground? And the answer is yes, you do. And so when it hits the ground is when y is equal to 0. So I'm going to put that right here. So that happens when y equals 0. And I'm going to solve this equation right here. And, it would be better for me, it's quadratic equation, when y is 0, if I wrote it in descending order like I do in my beginning algebra class. And so this is negative 16t squared plus 80t and my plus 176 equals 0, right? So setting y equals 0. So that's how it will look a little bit better. I would rather use the quadratic formula on it when I have when my coefficient, which is negative 16, is positive. So I would multiply this whole thing by -1. I tell you all of this, but I remember when someone I love dearly was in Calc 3. I won't say my nephew's name out there. And he came and he said to me, Donna, remind me what the quadratic formula is. And so I said to myself, I laughed, but I didn't laugh because I thought I was just like you. You and me are the same. And that's why I love you so much, my friend. So negative b, so that's 80, negative of negative 80 right there, plus or minus the square root of, and then this is 80 squared minus 4a 16 c negative 176, all divided by 2 times, right, a, which is 16. If you need to, you can go on YouTube and sing the quadratic formula to Pop Goes the Weasel, if that if that's helpful. Definitely you can. You could put it on your note sheet since I give you a note sheet if you like. Oh, I shouldn't have said that because what if I use this video on a semester when I've gotten mean and not letting people use a note sheet? Don't talk about that kind of thing. I push clear. Everybody should know the quadratic formula with or without a note sheet. So I have this underneath here. And let's see here. Square root. So nicely, my calculator simplifies that square root right there. So I could give the exact value, which a lot of times they put in the back of the book. And because we're math people, we appreciate the exact value where our colleagues in some of our colleagues don't appreciate it as much. So I could divide 16. Does 80 go 60? 16 divided by 80 go in there? Yeah, 5 times. So I could divide 16 out of 80. That's 5. My calculator, I think, will reduce this too. Your calculator will reduce that. 16 divided by 16 is 1. And so right here and 16, that's 2 down there. So there's the exact value right there in seconds. And then if we rounded it and gave an approximate, so I'm gonna put that in my calculator as well. So put that up in the numerator. I am writing where you can see, am I not? 5 plus the square root of 69. Downstairs a 2. I think the calculator might simplify that. Some of them won't simplify because it's just too gnarly. This one is, see how it says, this is what it should be the answer. And I have to push S to D to find the answer. 6 point, if I go to the 10th, it's 6.7 seconds. Now it wanted to know when it was on the ground. And I think if I use the negative, so if I come up here and I use the negative, I'm going to get something that's negative time. And S to D, and I get negative time. And so It's because the potato started on the top of the building that's happening. If the potato had started on the ground, one of our answers would have been 0, and the other answer would have been when it landed on the ground. What is the distance traveled by the potato? So now we know the time, right? So this is when it hits the ground, right? And so we want to find the range where the potato is. We know that the formula is x equals 80 times the square root of 3 multiplied by the time. And now we know, and this would be in feet, and now we know the time. And so x equals 80 square root of 3 times, and I always give, if I can, the exact, because I'm a math person. This might be pretty gnarly. I don't know. Maybe I don't want to do that exact. My calculator probably won't handle that exact. And so maybe I'm too tired to be too exact. Up in the numerator, I've had 80 and then the square root of 3. And then parentheses, I had to go over a little bit, 5 plus the square root of 69. And in the parentheses, so I had to arrow over. And in the denominator, I have 2. I decided to put it in one numerator like that. And the calculator says, yeah, I'm not going to give that to you in exact form. I'm not doing that. The calculator might have had too much of a day today too. I'm going to go to the 10th right there. And I don't know, probably 922 feet would probably be good enough, right? On this one. I wonder what your physics teacher would say. Okay, so what else do we got going here? What is the maximum height of the potato? So how high did the potato get at the very top? And so I'm going to put the height of the potato to remind you. Y equals was 176 plus 80t minus 16t squared. And this was in feet, right? That was the height of the potato. If we want to find the maximum height of the potato, can you guys think of a way that we can maximize this, find the maximum? Well, this thing right here is a parabola. And so if you found the vertex of that parabola, then you would maximize it. If it hadn't been a parabola, then a way that I could maximize it would be to find the first derivative. So I'm going to find the first derivative on this. Although if you wanted to, you could use the formula for finding the vertex of a parabola and do that. You do you. It's all good. It works out really good. So the derivative of this is 0. The derivative of this is 80. And then minus 32t. And so to find the max, I feel like I'm in Calc 1 right now, you let the derivative equal to 0. And so when I solve that, 80 minus 32t equals 0. And I can, 80 equals 32t. And then dividing by, so it would be 80 over 32 equals t. And so surely that reduces, right? 80, and this would be in seconds, 80 over 32. Oh, 2.5 seconds. Now, I don't think that's what they were asking, though. They asked, what is the max height? And now we found when it happens. It happens at 2.5 seconds. And so the max height, we can find that easily by plugging into y. So y equals 176. That was pretty nice that it's 2.5 seconds, right? 80t, 2.5, minus 16, 2.5 squared. And I'm going to put that in my formula. I got into my hole right there. Sorry about that. But it is, I just put it in that formula, right? And so 176 plus 80. I'm going to celebrate with some ice cream. This has been quite a weekend. A lot of grading, a lot of everything, maybe some ice cream. I don't know. Maybe I don't have any ice cream. So I'm getting y equals 276, and this would be in feet. So that's the highest it goes. So it started off on the top of the building at 170, oh, it's just coincidental. It was 176 feet to start with. And so it just went up another 100 feet is all that it did. So what is the speed of the potato on impact? So we want to know how fast is the potato going when it hits the ground? And so at just the moment it hits the ground, how fast was it going? It's not 0. That's the 1 second after it hit the ground. It's 0 is the speed of the potato. And so what is the speed of the potato on impact? Well, how are we going to find that? Oh, I remember this thing right here. If you take the derivative of that, that gives you the that's going to help me a lot, right? The speed, the derivative of this, and then the magnitude of that. So the magnitude of the velocity, right? And so, hey, this is going to work out pretty good for us, because we know when impact is, right? And so we'll be able to plug in, and because on impact it happens at 6.7 seconds, 5 plus the square root of 69 over 2. Okay, so that's what we're going to do. Now we know what x is, and we know what y is, so we're going to put that right here. So r at t equals, and whoops, I'm making it where you can't see, x, which was 80 square root of 3t I, plus, and then y, and then we've been using y here a lot, 176 plus 80t minus 16t squared j. Then the derivative, do you guys agree that it wouldn't be okay for me to put in the value of t until I've taken the derivative? I hope that you're agreeing with that, because it's true. And so I was going to take the derivative, and I didn't put my derivative marker, but I am going to. So the derivative of this part is easy. It's 80 square root of 3 I. And then the derivative of the next part's not too bad either. 0, 80, and negative 32 tj. And then now it would be okay for me, now that I found the derivative, because the velocity, I guess I didn't tell you the speed, is this right here is the velocity at t, right? And the speed is the magnitude of the velocity. And so now that we've taken the derivative, it would be okay for us to put in t. So if you wanted to plug in what t is right now, that would be okay, or you could wait. So speed equals, so your choice on whether you wait, this squared, 80 square root of 3 squared, plus this squared, right? So we did a lovely job at that. And then I'm just going to plug in what t is in my little calculator there, and put it in my calculator and let it figure it out. So remember that we can plug in t at any time. I'm going to plug it in now. So it's 5 plus the square root of 69 over 2. And I always put in exact, because I'm a math person, and I don't want any rounding error. And I remember that when I used to not put in exact, that I would get marked off in my physics class, which always made me mad for not using the exact value, and then rounding at the end. But that was just my professors at UCLA. I didn't take the physics at BC. That would have been a smart thing to do. If I would have been thinking, that's what I would have done. But at the time, I was thinking that I wasn't going to be a STEM major. when I was at BC, and it wasn't until I got to UCLA that I decided I was going to be a STEM major. So I took the calculus at BC, but I didn't take the physics or the chemistry. I took them at UCLA, and that was stupid. I should have taken them at BC. Um, because I would have been in smaller classes and would have learned more. Then I ended up learning more, and I'm not putting down anyone at BC or at UCLA. Everyone was super nice, but just huge, huge classes, and it just would have been a better learning experience. Okay, don't be talking and putting this in your calculator wrong. And I know my calculator keeps uh, not having enough light. This calculator probably needs, these calculators actually need battery in them. And so this one's probably running out of battery. I do that every now and then to my calculators. So I think I put that in my calculator right. How I'll know if I put it in right is if I get the same answer I got last semester, which is right there, 192 feet per second. So that's awesome. So that's the speed on impact. And so very good, very good. So that's the end of the potato example. Woo, for Valentine's Day. And so coming up. Oh my gosh, ice cream. No, no, no. Maybe I'll have an orange or an apple. Hmm. Maybe I'll just have some hot tea. I don't know. It's so cold. Hot tea would be good. Okay. See you in the next video.